Specification for Foundation Fieldbus Part 7, System Management Protocol. The System Management Protocol, SMP, is an essential service layer within the Foundation Fieldbus architecture, providing critical supervisory functions that ensure consistent network behavior, deterministic operation, and stable device coordination. Unlike the application layer, which supports user-driven services like control and data access, system management operates autonomously in the background, orchestrating device identity, scheduling, synchronization, and health across the Fieldbus segment. Its primary implementation mechanism is the System Management Kernel Protocol, SMKP, which interacts directly with the data link layer. One of the core responsibilities of the SMP is device identification and addressing. Every field device is assigned a physical device PD tag, a unique node address, and an immutable device identifier, device ID. The PD tag is a user-defined textual name used for operator reference, e.g. FT101. The node address is an 8-bit number used in communication, and the device ID is a manufacturer-assigned global identifier that never changes. SMP services allow correlation and conversion between these identifiers, ensuring seamless integration and reliable replacement procedures. Tag and address assignment occurs during commissioning or when a new device joins the network. Devices initially operate in a temporary address space, typically 0xF8 to 0xFB, and are discovered using a probe node PN and probe response PR exchange. System management services then assign permanent node addresses and PD tags based on system configuration. The assignment protocol ensures that device replacement can occur without disrupting existing configuration, provided that the new device has matching credentials and function block structures. A vital feature of SMP is function block scheduling and coordination. For precise and deterministic control, function blocks within and across devices must execute in synchrony. The SMP defines a macro cycle, a repeating time base that defines when each block is to execute and communicate. This is implemented through the function block schedule, which resides in the System Management Agent, SMA, of each device. The LAS, Link Active Scheduler, coordinates execution timing by broadcasting link scheduling time, LIME, to ensure all blocks align with the macro cycle. The System Management Agent also manages application time synchronization, which provides a unified time base across all segments in the system. This allows for consistent timestamping of process events, alarms, and diagnostics. While LS time is local to a segment and governs function block scheduling, application time is universal and used for system-wide time correlation. Synchronization is achieved through periodic time distribution messages from a designated time master, and devices update their internal clocks accordingly. SMP ensures device behavior during failure or abnormal conditions. If a device loses configuration, fails to respond, or behaves unexpectedly, the system can isolate, replace, or reconfigure it using SMKP services. System management maintains a live list of active devices, updated continuously by the LAS. Any change in the device list, such as a device leaving or joining, is broadcast to all LinkMaster-capable devices, ensuring redundancy and readiness for takeover if the LAS fails. SMP also manages download and initialization sequences. When a new or replacement device is added, system management ensures that all necessary parameters, schedules, and VCR configurations are downloaded before the device enters service. This includes validation of the device ID, verification of function block structures, and restoration of stored parameter values. Devices remain in out-of-service OS mode until properly initialized and synchronized with the system schedule. The context management functions within SMP enable logical connection establishment and termination between system components. This allows temporary service-level interactions, such as configuration sessions or diagnostic reads, to be conducted securely without disturbing the primary communication schedule or system stability. SMP manages these contexts, ensures they are valid, and handles their graceful closure. System management is also responsible for network-wide status monitoring, including error reporting, synchronization failures, and configuration mismatches. It supports alarm and event management via source sync communication, ensuring that issues are communicated in real time to the host or asset management systems. Events are time-stamped using synchronized time and flagged according to severity and acknowledgement status. Finally, SMP plays a central role in device replacement strategies. By retaining and mapping PD tags, node addresses, and block configurations, it supports plug-and-play replacement of faulty devices. When a replacement device is detected with a matching device ID or profile, SMP can automatically assign the correct address, download the appropriate configuration, and reintegrate the device into the network with minimal disruption. In summary, the system management protocol provides the supervisory intelligence that enables Foundation Fieldbus to function as a coordinated, time-sensitive, and self-maintaining automation network. Its services underpin everything from initial configuration and schedule alignment to live diagnostics and device recovery, making it indispensable for maintaining the integrity, reliability, and operational continuity of the Fieldbus environment. Specification for Foundation Fieldbus Part 8. High-Speed Ethernet, HSE. High-Speed Ethernet HSE is the backbone networking layer in Foundation Fieldbus that extends the capabilities of the traditional H1 31.25 kilopsec segments by providing high bandwidth, plant-wide digital communication over 100 megapsecond or higher Ethernet. Designed to integrate distributed control systems, advanced diagnostics, asset management, and enterprise-level applications, HSE bridges the field-level instrumentation network with supervisory systems using a unified and scalable digital architecture. HSE conforms to standard IEEE 802.3 Ethernet and IP protocols, allowing seamless interconnection with commercial networking infrastructure while preserving the deterministic behavior and object-oriented architecture of Foundation Fieldbus. Unlike H1 segments that connect low-speed field devices using a single twisted pair, HSE supports switched full duplex communication between control systems, H1 interface modules, and HSE devices via high-speed Ethernet links, typically using Cat6 or fiber optic cabling. The HSE network forms the plant-wide Fieldbus backbone and interconnects various system components including host systems, DCS PLC, Fieldbus interface modules, FIMs, remote I/O subsystems, engineering workstations, asset management systems, AMS, HSE-compatible field devices. One of the core advantages of HSE is its ability to aggregate and route data between multiple H1 segments through linking devices like the Fieldbus Linking Device, FLD, or FEM. These devices act as gateways, connecting multiple H1 trunks to the HSE backbone while translating H1 communication schedules into Ethernet frames. This approach reduces traffic congestion, localizes deterministic communication at the H1 level, and delivers high-speed supervisory access to all field data. HSE supports the same function block architecture as H1, preserving system-wide interoperability and distributed control philosophies. Control can be executed in HSE-capable devices or remain in the H1 level field devices. Time synchronization across both layers is maintained using SNTP, Simple Network Time Protocol, or PTP, Precision Time Protocol, to ensure consistent execution of scheduled tasks and alarm timestamping. The communication model in HSE also uses virtual communication relationships, VCRs, similar to H1 but adapted for IP-based routing. These include client-server interactions for asset management, publisher-subscriber for process variables, and event-driven messages for alarms and diagnostics. VLAN tagging and QoS, quality of service, mechanisms are used in the Ethernet infrastructure to prioritize critical messages like real-time data and system events. HSE introduces a significant enhancement in data throughput, enabling asset management systems and higher-level applications to retrieve rich datasets, such as device status, historical logs, calibration data, and advanced diagnostics without impacting the performance of the primary control loop. This segregation between control and supervisory layers is key to scalable system integration. HSE networks can be structured into star, ring, or mesh topologies using managed Ethernet switches. Redundancy mechanisms such as Rapid Spanning Tree Protocol, RSTP, Media Redundancy Protocol, MRP, or Parallel Redundancy Protocol, PRP, are implemented to provide network fault tolerance. These methods ensure communication continuity even in the event of a cable cut or switch failure, enhancing the system's reliability. Security in HSE is addressed through segmentation, firewalls, VLANs, and authentication protocols. Because HSE operates over standard Ethernet and IP, it must be secured against unauthorized access, denial of service attacks, and broadcast storms. Devices must support MAC filtering, IP access lists, and role-based authentication for configuration access. Control traffic should be isolated from enterprise IT traffic using a demilitarized zone (DMZ) architecture. HSE also enables centralized engineering and diagnostics, allowing remote configuration and monitoring of devices connected through multiple H1 segments. Configuration tools can use the HSE link to access device descriptions, DDs, perform loop checks, and view real-time device health across the entire plant. Software such as Field Device Tool, FDT, Device Type Manager, DTM, and asset management systems can operate over the HSE network for full lifecycle instrumentation support. In summary, high-speed Ethernet, HSE, transforms Foundation Fieldbus into a fully scalable, plant-wide control and information system. By preserving the advantages of distributed intelligence and deterministic control at the H1 level while leveraging the speed, openness, and bandwidth of Ethernet, HSE enables integration of control, diagnostics, and enterprise systems into a unified digital platform that meets the needs of modern industrial automation environments. Specification for Foundation Fieldbus Part 9. Virtual Field Devices, VFDs. Virtual Field Devices, VFDs, are the logical containers within Foundation Fieldbus devices that encapsulate all the functions, data objects, and services necessary for a device to participate in a Fieldbus network. While a physical device represents the hardware, the VFD is the digital model of that device from the network's perspective. It abstracts the internal resources, such as function blocks, transducer blocks, system management components, and communication interfaces, into a structured, addressable form that ensures interoperability and standardized behavior across the network. Every Foundation Fieldbus device contains at least one VFD, and some complex devices may contain multiple VFDs if they support multiple independent roles or control domains. Each VFD is uniquely addressable and supports consistent access to process variables, parameters, alarms, and configuration settings. The VFD is what host systems and other devices interact with when performing reads, writes, diagnostics, or control operations. This abstraction is critical to maintaining a vendor-neutral, standardized automation infrastructure. VFDs are composed of a series of standardized blocks, primarily including function blocks, FBs (TID). These execute control and processing logic such as analog input (AI), analog output (AO), proportional integral derivative (PID control), and signal selectors. Transducer blocks (TBs). These serve as the interface between the function blocks and the actual hardware sensors or actuators, translating raw signals into standardized parameters. System Management Agent (SMA). This block handles scheduling, device time synchronization, address management, and other system-level functions required for seamless integration into the Fieldbus segment. Each VFD has a well-defined object dictionary, which includes indexed references to all parameters, block instances, data structures, and access rights. These indices allow deterministic access by hosts or other devices, regardless of manufacturer. Using this structure, configuration tools and asset management systems can reliably navigate the VFD, interpret parameters, and modify settings without requiring custom drivers. VFDs support both static and dynamic data with real-time process variables updated on a schedule via publisher-subscriber communication and configuration parameters accessed asynchronously via client-server communication. Variables such as pressure, temperature, or valve position are maintained within specific function blocks in the VFD and are made available for scheduled communication through virtual communication relationships, VCRs. Another essential function of the VFD is mode management. Each VFD and the individual blocks within it supports operational modes such as auto, manual, out of service, and cascade. These modes control how the block interacts with the rest of the system and allow for safe commissioning, testing, and troubleshooting. For example, setting a block to out of service temporarily suspends its participation in scheduled control cycles while still allowing diagnostics and configuration access. Each VFD is assigned a unique object identifier and contains metadata such as device tag and description, manufacturer and model ID, software and hardware revision, serial number, last configuration timestamp. This information supports inventory tracking when calibration management and compliance auditing. VFDs also store status flags and diagnostic bits that indicate health, alarm conditions, communication errors, and internal consistency checks. These flags are continuously monitored by host systems and can trigger automatic alerts or maintenance tasks. VFDs facilitate plug-and-play replacement of field devices. When a new device is detected, the host can compare the new VFD's structure to that of the replaced unit, verify compatibility, and download saved configuration files. If the VFD profile and block arrangement match, the device can be reintegrated without manual reprogramming. This functionality significantly reduces downtime during maintenance and supports standardization across large facilities. Finally, VFDs are central to ensuring interoperability and future scalability. Because the behavior and structure of each VFD is defined by device descriptions, DDs, and capability files, CFFs, host systems can interact with them in a consistent, predictable manner. This makes Foundation Fieldbus an open and extensible platform where devices from multiple vendors can coexist, share control tasks, and evolve over time without architectural changes. In summary, virtual field devices serve as the digital intelligence of every Foundation Fieldbus device. By providing a standardized, structured, and scalable interface for control, diagnostics, and configuration, VFDs allow seamless integration, robust distributed automation, and simplified lifecycle management across the entire field instrumentation network.